Once students have been through the Systems, Signals, DSP and FFT pack, they can move on to the Communications and Digital Radio Techniques course. This course allows students to construct and experiment on a wide range of systems based on Sysblocks. Students use a panel with 3 Sysblocks on to create a sequence of communication modulators and encoders. They can add noise and then demodulate and decode the signals. In doing so, students understand the parameters of communication systems, including phased lock loop performance, signal to noise ratios, bit error rates, and the principles of digital radio techniques. The communication systems students investigate include PLLs, AM, FM, OOK, ASK, FSK, BPSK, QAM, QPSK and DSSS. Students work with pre-written programs for Sysblocks, but there is also plenty of chance for creative programming using Flowcode for the more advanced students who will find that the Sysblocks panel and Flowcode combination provide the perfect platform for experimentation with digital comms. The hardware platform includes 3 Sysblocks panels, encode modulate, decode demodulate, and a noise generator, and a mixer board. Welcome to a demonstration of Sysblocks for communications, or for teaching communications. And what I've got in front of me is I've got one of our Sysblocks communication panels, and on it you can see there are 3 Sysblocks board. We've got a modulator or encoder or transmitter, we've got a demodulator, decoder, receiver, we've got some noise, and we've got a mixer board. And the idea is that you can set up a communication system with a transmit, receive and noise, where the noise is mixed into the signal between the transmitter and receiver, and you can set up a lot of different communication systems and do experiments with it. The hardware comes with some curriculum, which we'll talk about later, but also some software, in this case Flowcode. And you can see here in front of you that here's a typical Flowcode program. And a Flowcode program consists of 2 parts. It consists of a data flow program, you can see here, and this is a mimic for the Sysblocks board itself with displays and encoders, switches and LEDs. And also there is a program that you can see here. Now the program is really simple. It basically has a main routine that just sets up the system itself, and then it has an interrupt service routine. And we're interrupting probably at a couple of 100,000 samples per second. And the interrupt service routine basically just runs a macro for each of these data flow icons that says effectively execute or do what you do. Now what I've got in the transmit Sysblock, I've got an amplitude modulation transmitter, and this program here is a receiver. So you can see in the AM receiver, we take the input signal, we rectify it, filter it, we multiply it by 2 and we put it onto the output. And if you're familiar with amplitude modulation receivers in a more analog sense, you'll know that an AM receiver is really quite a simple circuit consisting of a rectifying diode and a capacitor for a filter. And this mimics that, but in a digital domain. So the interrupt service routine kicks off at 200,000 samples a second. Each one of these icons executes and sends a signal from the input to the output. So, and what we do basically in the communications pack for Sysblocks is we provide a whole load of pre-written programs, each one of which teaches a particular aspect of communications. So in this case, there are 2 programs. I'm showing you the AM demodulator here, and what we ask students to do is just compile those programs to the Sysblocks target. So I'll just compile this to the receiver now. Okay, so we've compiled that program. I've got, going back to the equipment, going into the Sysblock transmitter, I've got a radio. On the receiver, I've got a couple of speakers. They're plugged into the line-in sockets in the Sysblock. The whole system's set up now. So if I just connect the channel by connecting one Sysblock to another, then you can hear the audio coming out.
Asked her if she could remember a public row like this before. Not on this scale.
So what you can hear is that the audio from the line-in is modulated in analog modulation. That's put out onto a single wire, that's received by the second Sysblock, and it's now demodulated and fed to a speaker. Now we can look at that on oscilloscopes and things, and we can put in waveforms, and we can teach all sorts of aspects about AM, and we can teach about FM as well. So we teach about how chips these days are at the heart of all modern radio systems. The days of analog circuitry to do AM and FM are pretty much gone. So having seen the demonstration of AM, what we do in the learning materials is take students through a number of concepts to look at digital communications. So we're looking at phase-locked loops, and we're looking in particular at phase modulation of various different kinds. Frequency modulation, phase modulation, quadrotra phase modulation, and octal phase modulation. And we take students through the various concepts. Again, what they do is they download different programs to the Sysblocks and carry out experiments, most of which involve an oscilloscope to look at signals. And then towards the end of the package, what we do with students is we start to explain to them how packets of information can be put together to transmit information between a transmitter and receiver, and they can be put together using the various different modulation schemes. And to do that, we have written this application. And in this application, you can choose a different carrier frequency, the baud rate, and you can choose some information which relates to the types of packets, the number of cycles of preamble, so the phase-locked loop can sync, and the group length, or the number of data bytes in a packet. And you can choose the modulation scheme. And so if we take these settings here for on-off keying, we can enter a string. In this case, hello world, and we can transmit that string between the transmitter and receiver. And this is where the third Sysblock comes in, because what we can do is we can inject noise into that signal, and we can see how robust the channel is. And if I just set up a beakerscope here, what I've got is I've got the blue trace here is the data output, and the red trace is the channel. And if we set it to have a single trigger, again, what I can do is I can transmit information using on-off keying, and I can see the data coming in. So this is the data which has been received by the receiver, and you can see with simple on-off keying, I've just got bursts of carrier there. Let's do the same thing again for amplitude shift keying, and we'll send that packet of data there. Here you can see that a 1 is represented by a large amplitude, and a 0 is represented by a small amplitude, so you can see how the amplitude shift keying works. So I can send a string, I can transmit and receive, and I can increase the amount of noise in the system. So we'll do that briefly for ASK. If I go to the noise generating system and I say that the noise level is, say, minus 12 dB, and I retransmit that, you should be able to see now that there are some errors in that transmission. Oh no, it's doing pretty well. So let's give it a few more dB of noise, at minus 6 dB, and we've got 7% errors there. So you can see the hello world is just a bit corrupted. So that's how that app works. And it gets really interesting when we start to move to the more complex phase shift keying systems. So in this case, let's just take a look at how QPSK is transmitted. So if I set up, I put the noise back down to 0 dB, I set up a simple transmission of QPSK, and if I trigger the scope again, and send a byte, you can see that now, of course, it's very difficult to see the phase shifts in the transmitted signal, but you can just see phase shifts at certain times. And so what we need now is a different way of viewing that. And what we can do here is we can add a new view, we'll add an XY view to the system, And what I'll do is rather than looking at the transmission data or the transmission signal and one of the outputs, what I'm going to do is just change the connections to the Sysblock, because the program puts out the I and Q channels on the receiver. And what we can do is we can use an XY plot to show the signals in a constellation diagram. So I'll just trigger that again and send a packet of data, and you should be able to see that there is a really nice constellation diagram showing the 4 points of the QPSK signal, and you can see the I and Q there. And what we get students to do is manually dissect a couple of packets so they can see how the data is transmitted in this particular case. And we can go up to 8 QPSK. Let's try that and see if that works. Again, let's trigger the scope and look for 8 QPSK and see the data there. So you can see the eight data points. And of course what the program is doing is it's detecting whether the data is at one of these points in the constellation, and then that allows it to regenerate the original data signal.